Hi, friend. Welcome to the lab. Today, with the help of a special guest, you'll be learning all about the mysterious photoelectric effect and how it can be explained. We'll then use your newfound knowledge to explore how solar panels generate electricity. This simulation uses voiceovers. If you don't have audio, click the speaker symbol in the top right corner of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will pop up whenever there are instructions to read. Select the audio setup you prefer. To mute individual audio options, simply select them. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect. Then let's get started with your first mission. I'm super excited to share my new project with you. I've spent the past few months constructing this time machine that you see in front of you. Can you imagine how easy it would be to teach the next generation of scientists if we had access to all the great minds of the past? Our special guest should be arriving any moment now. There's no one better to explain the photoelectric effect than the man who was awarded a Nobel Prize in Physics for doing just that, Albert Einstein.
Ooh, that tickled. What a peculiar experience. Hello there, it's lovely to meet you both.
Oh no, is everyone okay? It looks like we fried the time machine battery. This is not good at all. If we can't get this powered again, Einstein will be stuck in the present and the course of history will be altered forever. The solar farm outside should be enough to jumpstart the machine, but I'll need your help to set it all up. However, before you can do that, we need to continue this lesson, so you actually know how solar panels use the photoelectric effect to generate electricity. Are you ready to go, Albert?
I'm absolutely ready to go. This is all very exciting, isn't it? I believe you have a demonstration of the photoelectric effect prepared for us, Dr. One?
Let's all head over to the hollow table.
Before we dive into the experiment, I'll give you a little bit of context. In the early 1900s, most of our evidence pointed toward light being an electromagnetic wave. This model makes perfect sense in a lot of situations. For example, we can easily observe the refraction, diffraction, and interference of light as it propagates. If it did not have a wavelength, we would have no beautiful rainbows to enjoy. We were definitely still missing a piece of the puzzle, though. There are some processes that just can't be explained by this wave model of light, including the photoelectric effect. The photoelectric effect is the emission of electrons from a metal surface when it is illuminated. This process is called photoemission, and the electrons emitted in this manner are called photoelectrons. Negatively charged electrons are bound to metals by their attraction to positively charged ions. They are released from the surface when they absorb enough energy from the light to overcome this attraction. The minimum energy required for escape is called the work function, and its value varies from metal to metal. At first glance, this seems like it could be easily explained by the wave model. The electromagnetic waves transfer a continuous stream of energy to the surface, and once the total energy absorbed by the surface exceeds the work function, an electron is released. However, upon closer inspection, we discover that this is not how the system behaves. Clearly more research was needed, so I decided to conduct my own investigation. In 1905 I presented my alternative photon model of light to explain the phenomenon. People must have liked it a lot because I was awarded a Nobel Prize in Physics for it in 1921. Today I'll take you through the observations I made and explain how they lead me to my theory. Let's go. I'll just ask you one quick question before we move on. What is the photoelectric effect? That's right. This can easily be observed in the lab by shining ultraviolet light on a negatively charged zinc plate.
For our experiment, we have two metal plates and a light source. The plate on the right is positively charged, while the plate on the left is negatively charged and currently has a zinc surface. The light source we are using produces only one frequency of light at a time. We call this type of light source monochromatic. We will observe the photoelectric effect by shining the light on the left plate. Any photoelectrons will then be attracted towards the positive plate on the right and recaptured.
Excellent. First, let's consider what we would expect to see in the wave model. In the wave model, light transfers a continuous stream of energy. The energy delivered per unit area per unit time, its intensity, depends only on the amplitude and not on the frequency of the light. This means, firstly, that the rate of photoemission and the speed of the photoelectrons should increase with the light intensity, and secondly, that changing the frequency of the light should have no effect whatsoever. At low enough intensities, we also expect there to be a measurable time delay between the activation of the light and the first photoemission, as it takes longer for the total energy absorbed by the surface to exceed the work function.
That's a lot to look out for. Remember, you can check the theory pages during the experiment if you need a reminder.
Okay, I think we're ready to start the experiment. I'll guide you through the most important observations and write them down on this blackboard as we go along. First, let's try changing the frequency of the light. Notice how there is no photoemission until we raise the frequency of the light above a certain value. We call this the threshold frequency. In this case, we needed the light to be in the ultraviolet region. We also see that, once above this threshold, increasing the frequency further leads to faster photoelectrons. In other words, the kinetic energy of the photoelectrons depends on the frequency. Already, we have a conflict with the wave model. We expected the frequency of the light to have absolutely no effect on the photoelectric effect, yet it clearly does. Now, we should see how changing the intensity affects things. This time, I'll let you make your own observations. Let me know when you find something. What effect does changing the intensity have? Yes. Interestingly, if we increase the intensity of the light, the rate of photoemission increases as we expect, but there is no change in the photoelectron speed. We are supplying more energy to the plate per second, but it just results in more photoelectrons with the same kinetic energy. This suggests that we cannot just think of light as a continuous stream of energy and that the distribution of energy may be more complicated than that. Next, let's check how quickly the system reacts. Turn the light off and then on again whilst above the threshold frequency. Make sure the intensity is non-zero. Notice that there seems to be no delay between when we activate the light and when the photoemission begins. This is not entirely unexpected, as long as the delay becomes measurable as we lower the intensity. Determine if changing the intensity affects how quickly the system reacts. Let me know when you have an answer. Does changing the intensity affect the delay? That's right. Intensity has no effect on the delay. This is not what we expect in the wave model, where the delay should become measurable if we lower the intensity enough. You should check if it matters what the plate is made of. Change the plate metal and test to see if the system behaves any differently. Let me know what you find. What effect does changing the plate metal have? Exactly. If we switch to a plate with a higher work function, for example from zinc to gold, we see that the threshold frequency increases. This seems to suggest that threshold frequency has something to do with the work function. Well done. We've covered everything important. Now, it's time to make some sense of all these observations. So how do we explain the photoelectric effect? Clearly the wave model is not sufficient. The answer is my photon model. In this model, light consists of individual massless packets of energy, called photons, that travel at 300 million meters per second in a vacuum. A beam of light can then be thought of as many separate photons, each carrying a specific amount of energy, rather than a continuous stream of energy. Increasing the intensity now means increasing the number of photons being delivered per unit time per unit area. When one of these photons is absorbed, it transfers all of its energy at once. We can now think of the photoelectric effect as a one-on-one interaction between photons and electrons. When we shine light on a metal surface, individual photons are absorbed by individual electrons. The electron gains all of the photon's energy at once and is ejected if this energy exceeds the work function of the metal. Photons are very strange. When interacting with matter, during the photoelectric effect, for example, photons act as particles. However, when propagating through space, they act more like waves. This means that they have a frequency and a wavelength. Through further experiment, we can determine that the energy of each photon depends on its frequency. The higher the frequency of the photon, the more energy it has. In monochromatic light, all photons have the same frequency, f, meaning that they each carry the same energy. This results in a threshold frequency, f0, where the energy carried by each photon is equal to the work function. Below this frequency, none of the photons have enough energy to release an electron, so we see no photoemission.
We can switch the setup to photon mode to illustrate this. Slowing everything down a bit will help as well. Switch to slow motion mode.
Ah, that's much better. Now we can clearly see how each photon results in a photoelectron. This device truly is wonderful. So how do we explain the lack of delay? For monochromatic light that exceeds the threshold, every photon has enough energy to free an electron. All of the photon's energy is transferred instantly when it is absorbed by an electron, so there is no delay while waiting for the electron to gain enough energy. This means that as soon as photons strike the plate, photoemission occurs. Photons travel incredibly fast, so there is no measurable delay from travel time either, at least at these distances. When an electron absorbs a photon, it gains all its energy. If this energy is more than was needed to free the electron, any excess goes into its kinetic energy. This is why the photoelectrons get faster as we raise the frequency past the threshold. If we increase the intensity of the light, we increase the number of photons reaching the surface each second. More photons mean more photon-electron interactions, and as a result, more photoelectrons. Because the energy of the individual photons is unaffected by the intensity, the speed of the photoelectron stays the same. You can see this for yourself if you change the intensity on the hollow table setup. Hopefully everything makes perfect sense to you now. Before we finish, let's go through some quiz questions quickly. Remember, you can continue using the hollow table setup to help you answer the questions. A light source illuminates a metal plate. The frequency of the light is greater than the threshold frequency of the metal, so we see the emission of photoelectrons. What do we observe if the intensity of the light is decreased? Correct. The photoemission rate decreases. This is because, at lower intensities, fewer photons are delivered to the plate per unit area per unit time. This means fewer photon-electron interactions and, as a result, fewer photoelectrons being emitted. When we illuminate a metal surface with monochromatic light, we observe a threshold frequency below which no photoelectrons are emitted. Which of the following is not a reason for this threshold? Well done. We observe a threshold frequency for monochromatic light because below this frequency each photon carries less energy than the work function. You are observing the photoelectric effect by illuminating a metal surface. If the wave model is correct, what do we expect to be affected when you change the frequency of the light? Not this time. Remember, we are talking about what we expect to see in the wave model, not what we actually observe. This means you cannot use the hollow table setup to answer this question. Please try again and remember, you can check out the theory pages if you need more information. Well done. The energy delivered by a wave only depends on its amplitude, so it shouldn't matter what the frequency is. This is not actually what we see, of course. Did you know that Robert A. Millikan was so convinced that I was wrong that he spent an entire decade carefully trying to disprove my theory? After all that time, he just ended up proving me right. Ha. Oh no, what happened, Dr. One?
It looks like the machine is draining power from the lab. We need to hurry and set up the solar farm while we still have the chance. Head over to the solar farm controls. Solar power is a very important application of the photoelectric effect, now more than ever. The sun is an effectively unlimited source of clean energy that we can use, alongside other clean energy sources, to phase out the use of fossil fuels and protect our planet. The solar cells that make up solar panels use the photoelectric effect to convert light energy from the sun into electrical current that we can use to power our devices. Solar cells are made from a special type of material called a semiconductor. These are more conductive than insulators but less conductive than conductors. Solar cells typically use silicon semiconductors mixed with other elements like boron and phosphorus. Layers of this material are arranged so that electrons can only flow one way. When the electrons in a solar cell are struck by ultraviolet photons from the sun, they are not ejected from the semiconductor material but instead become free to move and are directed into a conductive wire. This flow of electrons is current. We want our solar cells to produce as much current as possible. To do this, we maximize the surface area of the cells that are exposed to the photons from the sun, and as a result, maximize the number of photoelectrons produced. We do this by connecting many solar cells together to form a solar panel which we then orient to directly face the sun. We can increase the current further by increasing the number of solar panels. We have lots of them on the solar farm outside. In order to use the solar farm to jumpstart the time machine, we have to make sure that all the solar panels are fully constructed and properly aligned with the sun. Use the solar farm controls to construct and align the solar panels. Fill the current meter by maximizing the surface area of the panels exposed to the sun. Great job! The solar farm is set up and ready to go. Look, the time machine is working. We have power. Before we get this show on the road, I'll just ask you one quick question. Which of these actions would not measurably increase the current output of a solar farm? Exactly. In order to produce as much current as possible, we want our solar panels to absorb as many ultraviolet photons from the sun as possible. The sun is a very long way away, so raising the panels further off the ground will have effectively no impact on the number of photons that they capture. We don't have much time, so we'll have to send you back straight away, Albert. Head over to the time machine.
Goodbye, my friends. I hope to see you again someday. I've had such a wonderful time.
Pull the lever. You did it. Einstein is safe. Thank you so much for all your help. I have no idea what I would have done without you. Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.